Okay. So last session we started Laplace transform here, and already we seen the definition. The definition of a Laplace transform is this one. Laplace of f of t. Yes, anyone? Laplace of f of t is defined as its integral 0 to infinity
0 to infinity
e raised to power st
minus st f of t dt. Yes, so someone said in the last session it's like a gamma function, but it is not a gamma function there. There is a difference in gamma. There is a f of t is always a algebraic there, like x raised to n there. So it's not a gamma function. So the function is said to be transformation if it is used for some special purposes. It has some uses there. So this function or this integral is some function, and that function is known as a Laplace transform. So when we evaluate this integral, we left with the function of s only. So already we discussed about this. T is the variable in time domain, where s is the variable in the frequency domain. In generally, these time and frequency words are used in signals and system. That means there is a subject in electrical. But in general, you can say T and S are variable in two different domains there. Two different planes are there. One is a T plane, a TF of T plane, and other is SFS plane. That is S and FS plane. So on x-axis we take the variable s, on y-axis we take f of s. Here on x-axis we take t, on y-axis we take f of t. And this Laplace is the transformation. It transforms our function in t domain to a s domain. Okay, so entirely our plane is changing. That xy plane is changing there. Okay, so that about the Laplace transform. Now, another thing we discussed in the last session, there are many functions whose Laplace does not exist because that functions does not exist, does not define. I use wrong word actually, does not define on the interval 0 to infinity. So this is the semi-open interval 0 to infinity. So 0 is included, that is important. So the function which is not defined 0 and onward, such a function's Laplace does not exist. So many examples we've seen in the last session. General examples whose Laplace does not exist are like algebraic function like t raised to minus n, which is actually 1 upon t raised to n. Then we have tan of t, cot of t, sec of t, cosec of t. So this function Laplace does not exist. So this is the first, this is the second set. Third set, it is a log of t. Log t, the Laplace will not exist there. Just like a trigonometric function, in a hyperbolic function we have tan hyperbolic t, cot hyperbolic t, sec hyperbolic t, cosec hyperbolic t. So these functions Laplace also does not exist. So there are a big set of the function whose Laplace does not exist, provided that function itself not defined on the interval 0 to infinity. Now if you observe, there are very few functions we have the Laplace there. So these are known as a Laplace of a standard function, known as a standard results. So we have to come to the standard results now. It is just like our standard results of derivative. If I ask you what is the derivative of say x raised to n, you can directly say n into x raised to n minus 1 without using the limit definition. You directly give me the answer because we use that table of standard results to write the derivatives. Same thing we have to do it whenever we have to write a Laplace of some function and that function is in the form of a standard form. You can use this standard result and we can write its Laplace. So here we have total 8 functions which are known as a standard results. So let me prove these results one by one. So the proof can be asked in the exam for 2 marks. Okay, the proof of these all 8 functions can be asked for the 2 marks in the final examination. The proof of all these functions is already there in the textbook, but yes, we'll do it here one by one quickly. It is not so difficult. So let me come to the first standard result. So I'll write it here. Okay. So I will take here the first proof. So I will take it here. You can write a proof of a standard results. And the first one, we start as a Laplace of 1. Laplace of 1 is equal to. So how to start? Yes, anyone? How to get the Laplace of 1? Only one thing is in our hand, and that's a definition. Okay, definition of Laplace. So this Laplace of 1, by definition of Laplace, is 0 to infinity e raised to minus st, and now f of t. In this case, f of t is itself 1. So it is 1 dt. So what's the integration now? What is the integration of e raised to minus st? Well, 1 is like a constant.
Sir, minus s e to the power minus st.
E raised to minus st into minus s.
Upon s, sir.
Yes, upon minus s, because
minus
it's
s.
integration. So,
Minus s.
correct. Now, what will be the value for upper limit? These limits are for variable t. So we'll replace t by infinity. It comes e raised to minus infinity.
0.
0. Very good. And what about e raised to 0?
1.
Sir.
Yes, lower limit of the minus sign, and this is a 1. So it is 1 upon minus s as it is. So we get as a 1 by s. So you should remember now, Laplace of 1 is 1 by s. Laplace of 1 is a 1 by s. That you should remember here. Okay, those who are interested, they can note down it so that we can prove the next result there. Once you finish, tell me so that we'll move to the next question then. Okay, finished. Very good. So, can I write the second?
Yes, sir.
Okay. So second property is here. That is a. Just a minute. This is the Laplace of e raised to at. Now we are coming here Laplace of exponential function. So Laplace of e raised to at, by definition, because only definition is in our hand, we can start with the definition to get the Laplace of all these functions. Integral 0 to infinity e raised to minus st. F of t is in this case is e raised to at only, and dt. That's one. Now if we combine the base, yes,
So minus st plus at, e to the power minus st plus at.
very good, because base is the same, you can add the indices e raised to minus st plus at dt. Now the next step, we have to let me take t as a common. So e raised to minus. Now one more important thing, as we want that this integral should converge, and if integral is converge, we should not have e raised to plus infinity. If we have e raised to infinity, it is infinity only. E raised to minus infinity is only 0. So here minus sign should be outside. So I will take that minus so that I will tell you one condition also. So this
S minus
minus,
s.
yes, s minus a into t, is that?
Yes, sir.
Now tell me the integration.
Sir, e raised to minus t, s minus a upon minus s minus a.
Upon s minus a. Okay, upon s minus a. And limits are again that same 0 to infinity. If you put upper
Minus-
limit, as usual, e raised to minus infinity goes to the 0.
0.
But there is one condition. When we say it is a 0, what should be that condition? Can anyone tell me?
So sir, s minus a should be positive.
Very good. That's correct one. So this is unwritten conditions everywhere. There is no need to write all these conditions because nowhere it is written. So you should know, but that s minus a is a positive, then only you will get e raised to minus infinity there. Okay, if s minus a is a negative, yes, this integral will diverge and you get the answer as infinity. So Laplace will not exist there. So no need to write anything there.
Should
Just
be a
say,
minus sign.
yes, this minus sign indicates it's a e raised to minus infinity. That's a 0 upper limit. Lower limit of the minus sign, e raised to 0 is 1. And here, yes, I forgot that minus sign, correct. Okay, someone said me. So it's minus of s minus a. And we got the answer as 1 upon s minus a. So Laplace of e raised to at, this Laplace of e raised to at is 1 upon s minus a. Laplace of e raised to at is 1 upon s minus a. That's the second important standard result. Requires number of times. Many of the questions we use the Laplace of exponential function. Can anyone tell me what will be the Laplace of e raised to minus at? This will go
Sir,
in a,
sign
yes,
will change.
little louder.
Sir, I think the sign will change and it will become 1 by a minus s. Will it be?
Not correct, not correct.
Sir, both the terms will come plus.
Yes, both the term will
1 by
come
s
plus
plus
1
a.
upon s plus a. Let I show you, those who have the doubt here. So here you will have e raised to minus at, then this become e raised to minus at there. So this sign will be the minus. As that is a minus, minus is taken common, here it become s plus a. Okay, this is s plus a, this is s plus a, and this will be everywhere that s plus a is there. So this way you get Laplace of e raised to minus at. Laplace of e raised to minus at is 1 upon s plus a. So two results are there for exponential. You should know Laplace of e raised to at. Laplace of e raised to at is 1 upon s minus a, while Laplace of e raised to minus at is 1 upon s plus a. Okay. As there are very limited function, a minus s is not correct. As these are standard result, you have to, if you have to write the Sanchit answer as 1 upon a minus s, then you should write where a minus s is greater than 0. Okay, a minus s is greater than 0, but generally s is a variable. So as these are standard results, we should write in a standard form only, whatever the standard results were given. That way also you can write it, but you have to mention the condition then. Okay. Now one important thing, already we discussed that there is algebraic function, trigonometric function, and hyperbolic function whose Laplace exists. So hardly there are 8 functions. So later on we have questions whose Laplace we have to calculate is just combination of these functions. These are the combination of that. Okay, we'll come to that later on. So I'll move to the third result then. Can I? Are you completed?
Yes, sir.
Done. Very good. So third one. Let I take the third result. Yes, anyone guess?
Sin 80.
Yes, trigonometry is there, correct. But before trigonometry, I will take one here, that is algebraic. Laplace of t raised to n. Laplace of t raised to n. So this will come as integral 0 to infinity e raised to minus st t raised to n dt. No, someone said st is equal to m, then it is a gamma. That is it a, that is not for all example, only this example, correct? I think yes, for this result, yes, it is in gamma. Now you can identify whatever the integral comes here, this is in the gamma form, gamma function. So here is a use of that gamma function to get the Laplace of t raised to n. We already observed in the last semester, integral 0 to infinity e raised to minus x, x raised to n minus 1 dx is a gamma n. So this is the thing that we already learned in the last semester. So we can convert this integral in that form. That integral we can convert in the form of e raised to minus x there. So let st is equal to x. Let that st is equal to x. So this will give us dt. The value actually the value of t is x by s, and dt is equal to dx upon s, because t is equal to x by s. Can you check the limit? When s is a 0, when s is a 0, x is 0. When s is infinity, that x is also not s. My mistake, actually t is a variable. When t is a 0, x is a 0. When t is infinity, that x is infinity there. Therefore, this Laplace of t raised to n will become, its integral 0 to infinity, the same. This will become e raised to minus x. Okay, this is the result that we are going to use it. This is not a part of the proof. Okay, e raised to minus x, value of t is x upon s raised to n, and this is a dx upon s. So next step, yes.
Sir, we'll take out the constant terms 1 upon s n plus 1 raised to the
Yes,
power n
correct.
plus
1
1.
upon s raised to n plus 1 is a constant. Very good, correct. And we left with integral 0 to infinity e raised to minus x raised to n dx. And what is the value of that? Value of that integral?
Gamma n plus 1.
Yes, very good. Gamma n plus 1 upon s raised to n plus 1. So Laplace of t raised to n is a gamma n plus 1 upon s raised to n plus 1. That's the answer. But if n is integer, gamma n plus 1 can be written as
N factorial.
yes, n factorial upon s raised to n plus 1. So there are two formulas for Laplace of t raised to n. Remember, Laplace of t raised to n is a gamma n plus 1 upon s raised to n plus 1, provided that is a fraction. If n is a fraction, we cannot write in a factorial form. But if n is a integer, then we can write that gamma n plus 1 as a n factorial. Okay, so depending on, so if you have to find out the Laplace of t raised to half root t, so which formula you will use? Laplace of t raised to half, you should use a gamma, na? Because it's in fraction. But if you have to find out Laplace of t square, then you use a factorial formula. That's one. No by parts. Okay, I think Asif is saying using by part we can solve this. There is no need of a by part. It is just gamma function. Use of a gamma function is here. That gives you the answer. Once you complete, tell me. Okay, done. So few of you said done on the chat here. So let I move to the next property. Pardon? Okay, so I'll move next result then. Okay, I think the three proof we completed here. The fourth one that I will write it here as, yes, Laplace of sine 80 now. Laplace of sine 80. So by definition, it says it's integral 0 to infinity e raised to minus st f of t. In this case, f of t is a sine 80 dt. So that about a definition. Now, how to integrate?
E to the power x into sine bx wala
Yes,
integration.
very good, very good. So these are the few prerequisite formulae already I given, and you should focus on that, and that formulas are enough for Laplace transform here. So by comparing that formula, what will be the integration? It is one step then.
1 upon s square plus a square.
Yes, e raised to minus st
Sorry.
upon s
Yes,
square
sir.
plus a square.
Minus s sine 80
Very good.
minus
A cos 80.
A
Very
cos
good.
80.
Minus a cos 80. Nice. So just it is the use of a formula only, because this question is for the 2 mark in the exam if it comes. Generally simple questions are coming in the exam, like Laplace of 1, Laplace of e raised to 80, that are asked. These never asked right in the old question paper, but if it comes, you should know. So just now replace a limit, upper limit e raised to minus infinity. This is a 0. Okay, when you replace this infinity to the exponential here, so there become indeterminate form. No need to go in that. It's a 0. Upper limit, it's a 0. Lower limit have the minus sign. Now e raised to 0 is a 1. This is 1 upon s square plus a square. Now we are going to replace that t by 0. What is the sine 0? Sine
0,
0 and cos 0 is 1. So it is a
1.
0 minus a. So we get answer a upon s square plus a square. So the result that we got, it has a Laplace of sine 80. Laplace of sine 80 is a upon s square plus a square. That's the answer. A upon s square plus a square. Correct, Asif. Now the proof of the next 3 results are similar. We're left with cos 80, sine hyperbolic 80 and cos hyperbolic 80. Okay, so the proof are exactly similar. I will tell you one by one. Once you finish this, tell me, so that we move to the Laplace of sine hyperbolic 80 first. We'll do it at sine hyperbolic 80. Okay, so if we have to do for, I'm writing here fifth in the same one. So I will show you the change. You take it like a self-study or like a homework. Later on you can do it. So if we want Laplace of sine hyperbolic 80, so here is h, sine h80. So integral 0 to infinity e raised to minus 80 sine h80. That will be the change, sine hyperbolic 80. H is not a constant, we already seen in the last semester. Now there is a change in a formula. This in this side, okay, e raised to minus st upon this s square minus a square is there, okay, or I will say e raised to ax upon a square minus b square is there. That is only the change. E raised to ax upon a square minus b square. Remaining formulas are same like a trigonometric function. So this plus will change to the minus s square minus a square. All these only just replace corresponding trigonometry by hyperbolic. Sine hyperbolic 80, cos hyperbolic 80. So this will be the minus, this will be the minus, and this will be the minus there. And then when we have sine hyperbolic 80, Laplace of sine hyperbolic 80 is a upon s square minus a square. A upon s square minus a square. Is that clear? Is the result of sine hyperbolic 80 is clear? There is a change in outside only, that is 1 upon s square minus a square. Other functions just replace circular function by corresponding hyperbolic function. Got it? And exactly same thing is there for cos and cos hyperbolic 80. Cos and cos hyperbolic 80. Any doubt, anyone?
Please repeat it again.
If we have to find the Laplace of sine hyperbolic 80, just do the example of sine 80 only. Replace every circular function by corresponding hyperbolic function. Means here is a sine hyperbolic 80. So sine hyperbolic 80 and cos hyperbolic 80 is there. and just outside there is a minus sign. Is it clear, Swapnil? Or I should write it separately? Can I write it newly? Got it, okay. Same we will do with, yes, cos 80, correct one. Same we have to do it with cos 80 and cos hyperbolic 80 also, correct. Okay, let I show you this cos 80 only. So 6, okay, just a minute. Proofs are not necessary, but yes, in our syllabus it is not written without proof. Okay, these proofs are not written as a without proof, so I'm taking here. By chance, if it comes in the exam, you should know how to do it because it is one line proof only. So if we have to find the Laplace of cos 80 here, or let I show you cos hyperbolic 80. So cos hyperbolic 80. Suppose we want Laplace of cos hyperbolic 80, it's an integral 0 to infinity e raised to minus st cos hyperbolic 80 dt. Now the formula is, yes, can anyone tell me? It is similar to the cos 80 only. So e raised to minus st divided by,
H square plus k square.
here
S
is not
square
plus
plus
now. As it is hyperbolic, you should say s square minus a square. Whenever it is hyperbolic, denominator is a negative. That's one change. Then a, the value of a is a minus s
minus S.
cos hyperbolic 80. Then
Plus.
plus b, the value of b is a here. A sin hyperbolic 80.
Sin hyperbolic 80.
That's one. Okay, and the limits as usual, that's a 0 to infinity there. Okay, it's a 0 to infinity. Now put the limits. Upper limit as usual e raised to minus infinity is a 0. Lower limit have the minus sign and is 1 upon s square minus a square. And let me replace here cos hyperbolic 0. Cos hyperbolic 0 is 1. So this is minus s, and sin hyperbolic 0 is a 0. So we got here s upon s square minus a square. So Laplace of cos hyperbolic 80, Laplace of cos hyperbolic 80 is s upon s square minus a square. Can anyone tell me what should be the Laplace of cos 80? Laplace of cos 80?
S square plus S.
S upon s square plus a square. Okay, denominator is only plus. S upon s square plus a square. What is the change in Laplace of sin 80 and cos 80?
Sir, a upon x square plus
Yes,
s
there
square.
is a and here is s. Okay, so that's only in the numerator there is a change. Okay. Yes, very good. So that about the proof of all the standard results. So all these standard results are like that only. So let I show you the standard results again. So here are the standard results. Can you see it? Laplace of 1 upon s. Laplace of e raised to 80 is 1 upon s minus a. Laplace of e raised to minus 80 is 1 upon s plus a. Laplace of t raised to n, gamma n plus 1 upon s raised to n plus 1, or n factorial upon s raised to n plus 1, depending on fraction or integer. And last, Laplace of sin 80, a upon s square plus a square. Cos 80 is s upon s square plus a square. Laplace of sin hyperbolic 80 is a upon s square minus a square. Laplace of cos hyperbolic 80 is s upon s square minus a square. Actually, the proof of sin hyperbolic 80 Laplace can be proved in another way also. And can anyone tell me what will be the second way to prove the Laplace of sin hyperbolic 80 is this one, or cos hyperbolic 80 is this one? So to get a Laplace of this sin hyperbolic 80 as this one, you can use a definition. And what is the definition of sin hyperbolic 80? Suppose you want Laplace of sin hyperbolic 80. What's the definition of sin hyperbolic 80? Euler's definition last semester.
Sir, x raised to power h
E raised to 80
Minus
e raised to minus
A
80
minus 80 upon
raised to
2.
minus 80 upon 2.
2.
And if you simplify this, you will get this answer only, because you know now Laplace is a linear operator. Laplace is linear operator. The meaning is a constant can be written outside like this. This 1 by 2 can be taken outside the Laplace operator like a derivative, and we left with the Laplace of e raised to at minus Laplace of e raised to minus at. And now we can write a Laplace of that e raised to at, which is 1 upon s minus a minus 1 upon s plus a. And now you have to cross multiply, simplify, you get this answer. You can check. Is that? Are you getting?
Yes, sir.
Okay. So this is another way to prove this result. Yes, this is obviously easy. Correct, Asif. If you want a Laplace of sine hyperbolic at or cos hyperbolic at, whenever you have to find the Laplace of hyperbolic function, another way you can use a Euler's definition of hyperbolic. Okay, so that is one of the simple way. But when the question in the numerical, if we want Laplace of sine and cos hyperbolic, directly we have to use these results. This one, no need to prove there. Okay, no need to prove these results in the numericals. Yes, Rohan is asking which one we should do in the exam. Whatever the way you think simple. Okay, both are correct. You will get full marks for both the proofs there. So choice is yours. You can use Euler's definition or you can use a standard formula. Okay. A similar proof is for cos hyperbolic at. Euler's definition of cos hyperbolic at will be e raised to at plus e raised to minus at upon 2. That is a formula for cos hyperbolic at. Okay, so that about standard results. Now we are moving here on the type 2, which is mainly in the exam coming for 2 marks. So the 2-mark questions are generally, if you observe in old question paper, they are either coming as a proof of the property or very simple questions where you have to use a trigonometric identity and a standard table to get the Laplace of a given function. Now here is the first thing that written on the screen. This is actually the first property. This first property of Laplace operator known as a linearity property. Laplace of a f1t plus b f2t is a times Laplace of f1t. Actually, this f1s is the Laplace of f1t and f2s is the Laplace of f2t. Okay. So Laplace is a linear operator. It is just like, it is exactly similar to the differential operator or integral operator, where we have that derivative of addition is the addition of their derivatives. Okay, integration of addition is the integration of their separate function. So same thing like Laplace. Laplace is also a linear operator. Along with this, we require these 7 trigonometric identities. Okay, maximum these 7, not any other identity you require in Laplace. One is a conversion of cos square theta into addition. Cos square theta is 1 plus cos 2 theta upon 2. Sin square theta is 1 minus cos 2 theta upon 2. Again, this formula, triple angle formula, we require actually a sin cube theta in terms of sin 3 theta. This formula we use in reverse way later on. Sin 3 theta is a 3 sin theta minus 4 sin cube theta, while cos 3 theta is a 4 cos cube theta minus 3 cos theta. And then this is the defactorization formula where we convert multiplication to the addition. Whenever we require sin a into cos b, we can write it as 1 by 2 times sin of a plus b plus sin of a minus b, that way. Okay, so that about 7 trigonometric identities there. So already this PPT with you, I shared it on WhatsApp group, so you can note down later on in your notebook. Okay, so let me see simple questions then. These are very simple questions here which we have. So questions in the exam are coming like this. So these are the questions already asked in old question paper for 2 marks. The question will be like this: find the Laplace of sin 3t into sin 4t. Yes, which formula we should use? Anyone?
Sir,
Don't.
2 sin 3t sin 4t.
Huh?
2 sine 7 sine 70.
Okay, is that not
That
correct? Not correct. So yes, obviously we have to convert this
Multi-
multiplication to the addition to use a standard result. Don't. So let me say first. Let me write a formula. That's better always. As sine A
oh,
into
super.
sine B is 1 by 2 times. Yes, what is the formula? Cos of. It is not in sine. Is it
Uh,
A plus B.
cos A plus B? Is that?
cos a minus b minus
Plus
cos a.
See, someone is giving me cos A plus B. Now A minus B. Which one is correct? Cos of A minus B minus cos
Minus
of
cos
A plus B. Is that? Now you can cross check also. We know that cos of A plus B is cos A cos B minus sin A sin B. So whatever the given formula is correct. Okay. So this is the correct formula. You should know this formula is multiplication to the addition. Therefore, sin 3t into sin 4t will become 1 by 2 times cos of A minus B. Now cos of 3t minus 4t, that will become cos of minus t, but cos of minus theta is cos theta, so you can write it cos t only, minus cos of 7t. So last step, therefore take Laplace on both sides. Laplace of sin 3t into sin 4t will become, we are taking Laplace on the both side, and as the Laplace is a linear operator, what we can do it, we can write 1 by 2 as it is, and we can write it here. This is the Laplace of cos t. Okay, I'm cos of minus theta is cos theta, so I'm not writing that minus sign. Laplace of cos t minus Laplace of cos of 7t. That about just a linearity property of a Laplace operator. In the exam, there is no need to write this step also. If you want to drop this step and you write directly the answer like this, 1 by 2, and if you write the answer, Laplace of sin 3t into sin 4t is equal to 1 by 2. Now what is the Laplace of cos t? Yes, anyone? Laplace of cos t.
S by S
Uh,
plus
s upon s square plus a square. What is the value of a here? A is 1.
1.
1.
So that's 1. And what about this second? S upon,
S
S
square
upon a
plus
square plus
47, 49.
49.
and that is the final answer. So just you can highlight this answer, because always these answers are comes like this only. No need to cross multiply, no need to simplify. Keep as it is. Keep as it is. So this will be our Laplace. This will be the Laplace of sin 3t into sin 4t. Okay. Don't simplify. Sometimes if you simplify and examiner doesn't have that answer, he will confuse there. So keep as it is. Whatever the answers in the Laplace you will get, keep in the fraction as it is. Do not cross multiply. Do not simplify there. Unless the question is a show that. Any doubt, anyone? So type 1 questions are based on trigonometric identities only. You have to use sine square theta, cos square theta, sine cube theta, cos cube theta, or sine A cos B, cos A cos B, and sine A sine B. So these 7 formulas only we require for type number 2 here. So if you complete it, tell me. I will show you the next question, and I want the answer from you then for next question. Yes, okay, 1 minute, I will give it.
done.
Okay, done. Very good. So I will show you a next question here. Okay, complete it. I will give 1 minute to complete you first. You can tell me the answer also. Yes, anyone? Finished? 1 by 2, 1 plus cos 80, someone written, that's not answer.
1 by 2, so
Yes,
1
okay.
by s plus s by s square plus 64.
Okay, good. So let me see here. 1 by 2, 1 upon s plus s upon s square plus 4. That's the answer written, but I think s square plus 4 will not come.
64, 64.
64 will be the correct answer. Correct. I think Asif, you should write 64 there. So that's correct. So it is just based on the trigonometric identity. So we should you can write first trigonometric identity. Okay, like as cos square theta is 1 plus cos 2 theta upon 2. So this gives us Laplace of cos square 4t will become Laplace of 1 plus cos of 8t divided by 2. 1 by 2 is a constant, comes out. Then we left Laplace of 1. Laplace of 1 is 1 upon s, and Laplace of cos 80 is s upon s square plus 64. And that's the answer. So hardly in 2 steps you get the answers, and you have to keep as it is only. So this is the correct answer. 1 upon s plus s upon s square plus 64, not 16. Okay. Is it 16 or 64? Someone is written there 16 again. 4 is obviously not correct. 64 is the correct answer. Okay, good. Yes, Rishang and Dilshad, you are correct. 64. Yes, 1 upon 2 into 1 by s plus s upon s square plus 64. Correct. Correct, Asim. So do the step by step. Yes, we dropped one step here. We directly written the answer. Means we not drop actually. The linearity property that no need to write it separately. You can write the answer like this also in the exam. Okay. So can we move to the next part then? If you've done, if you finished it.
Yes, sir.
Okay. Good. Now the properties here. We have the properties. Or we are going to start the type 3 here. Laplace transform by using the properties. Type 1, we just seen one example, only one example of a type 1, where we use a Laplace transform by definition. When we use a definition, mainly whenever the function is break into the parts, like function is defined on interval 0 to 1 and then 1 to infinity separately. Because of that, we cannot use the standard results and we use a definition there. But I already told on type 1, there is never a question in the exam. Type 2, Laplace transform by trigonometric identities. That question generally comes for 2 marks. And here is on the type 3, which is the most important type, Laplace transform by using the properties. There are near about 7 properties again. Okay, 7 properties for Laplace. So one 5-mark question generally always come on a Laplace transform by using the properties. Out of that 7 properties, first 3 properties I written on the screen here. First property is the linearity. We already discussed about it. Second property, I will tell you. Now, before we move to the second property, I will tell you one thing here. You'll observe the Laplace of which functions exist. Laplace of t raised to n exist. Laplace of e raised to at exist. And Laplace of sin 80 cos 80 exists, or sin hyperbolic 80 cos hyperbolic 80 exists. Now next part that we have is, suppose these functions comes in addition. Find the Laplace of t raised to n plus e raised to at plus sin hyperbolic 80 and sin 80. You can take Laplace of these terms one by one by linearity property. By the linearity property. But if it comes in multiplication, then only we require these properties. For example, suppose we are interested to find Laplace of t raised to n into e raised to at. or Laplace of e raised to at into sin at, that way. So that time these properties are useful, and these properties are self-explanatory. Just you'll observe the property number 2 says, whenever exponential function into f of t comes, whenever e raised to at into f of t comes, then we have to use the shifting property, first shifting property. Why the name given as a first shifting? Because it shifts the variable in the s domain. It shifts the variable in s domain from s to s plus a. Let I tell you what is that property first. So if we know the Laplace of f of t, suppose we know the Laplace of f of t is f of s. Laplace of f of t is f of s. If we know this one, then we can write Laplace of e raised to at into f of t as f of s minus a. F of s minus a. Whenever you multiply by e raised to at, shift s to s minus a and you get directly the answer. Or Laplace of e raised to minus at into f of t. When you multiply by e raised to minus at, you have to shift s to s plus a. Shift s to s plus a. That about a first shifting property. Okay. Once we see the examples, it becomes more clear. And now in the syllabus, all these properties are written without proof. Okay, the properties are without proof. The proof of these properties will not come in the exam, so we'll not go in that. All the proofs are already available in the textbook. Those who are interested, they can go through the proofs. But all the proofs are given just by definition of Laplace only. Okay. So this is the first shifting property. The shifting is done in S domain. In first shifting, the shifting is done in S domain there. Any doubt in the first property? That second property actually, the first shifting. We'll do the example, then it becomes more clear. And let I tell you the third property also with second. Third property, the second shifting. Now second shifting property actually works that shifting is in t domain. If t is in the form of f of t minus a, then only if t is in the form of f of t minus a for t greater than a and 0 for t less than a, then only we can use a second shifting property. Again, there is not a single example asked on second shifting property in the last 5-7 years. Okay, in last 5 to 7 years, there is not a question on the second shifting property. The questions mainly comes on first shifting and the other properties there. But as it is a part of syllabus, yes, we'll complete it. Second shifting also. Let I explain you the second shifting property. The second shifting property says if we have some function g of t, if this function g of t is in the form of f of t minus a for t greater than a only. Okay, f of t minus a for t greater than a only and 0 for t less than a, then Laplace of g of t, that Laplace of the function g of t, okay, the Laplace of the function g of t is e raised to minus as into Laplace of that f of t. Laplace of that f of t. But what is that f of t here? This f of t is obtained from f of t minus a. We are given there f of t minus a and we want f of t. So just we replace t minus a by t. If we replace t minus a by t, we get f of t and we take Laplace of f of t here. That is fs. This fs is nothing but Laplace of e raised to minus, Laplace of f of t. That is fs. We'll come to this property with example. Okay, both the properties, we'll see the example. It becomes more clear then. So the question is on the screen. Can anyone tell me which property should we use to get the Laplace of the given function? The question is evaluate a Laplace of e raised to minus 3t into 2 times cos 5t minus 3 times sin 5t. Which properties we require? Yes.
fs plus a.
Name of the property. First shifting, yes, Asif is saying first shifting and linearity also. Rohan, yes, in more detail it is given. First shifting plus linearity, that is the correct answer. Linearity property also we are going to use it indirectly. So to use a first shifting property, always you have to, whatever the function we are given, you should clearly observe and you should decide what should be f of t. What should be f of t? so that we can use a shifting later on. So just we have to ignore the exponential function. Ignore this exponential function and find the Laplace of remaining, and then we can use the first shifting property. So to get, so we should start with that only. Consider Laplace of 2 cos phi ut, 2 cos phi ut minus 3 times sin phi ut. Consider the Laplace of 2 cos phi ut minus 3 times sin phi ut. So that we can consider as f of t also. Okay. So or you can say you can start like this also. I will start like this. Let f of t is 2 times cos phi ut minus 3 times sin phi ut. That's one. Therefore Laplace of f of t is, yes, anyone? What should be the answer? This 2 is a constant as it is. What is the Laplace of cos phi ut? What's the Laplace of this cos phi ut?
1 by s plus s upon s square plus 25.
No, there is no 1 by s. Why you are saying 1 by s? S upon
So S by
S
S
upon s.
minus
s
25.
square plus 25. That's
Square
the Laplace of cos phi ut.
20.
Now what is the Laplace of sin phi ut?
sir,
A upon s.
A is a phi, no?
yes.
So here is s upon s square plus 25, and here is phi upon s square plus 25. That is the Laplace of sin phi ut. You will observe the denominator is the same. So can I write Laplace of f of t as 2s minus 15 divided by s square plus 25. So we got this Laplace of some f of t. We got it as a f of s. We say let us say this is some function fs. We just given the name to that function. You can write it by f of s, phi of s, or any other symbol. Okay, so that way. Therefore by first shifting now,
Sir, this last step, please tell once again, sir.
this is just common denominator is there, na? This
Okay.
2s minus 15 is only written numerator. Denominator is the same, so just we kept the numerator collected together. So by first shifting property, yes, anyone? What should be Laplace of e raised to minus 3t into f of t? Yes.
Sir, f s plus a.
Now what is a here?
Sir, minus 3.
3. So it is
3.
it f of s
S
plus 3
plus
or s
3.
minus 3? Is it s plus
S
3
plus
now?
3. Yes.
So by first shifting property, if Laplace of f of t is fs, if Laplace of f of t is fs, Laplace of e raised to minus at into ft is f of s plus a. So just to replace that a by 3, and now this is our fs, so it should be f of s plus 3, 2 times s plus 3 minus 15 divided by s plus 3 bracket square plus 25, and you have to keep this as an answer only. Don't try to simplify this. Never you should simplify these answers in the exam. You have to keep the answers in that format, so examiner comes to know that you find the Laplace of f of t first, and lastly you return shifting part. Okay, first shifting part there. Yes, the simplified is also the part there, but there is no need of simplification. No need to write like 2s plus 6 minus 15 and then that way. Yes, firstly we use linearity property and then first shifting. Yes, Praneeth, is there any problem in linearity? First shifting is a very straightforward there. First shifting is a very straightforward. If we know the Laplace of f of t as fs, Laplace of e raised to minus at into ft, directly we can write it as f of s plus a. So every s you have to replace by s plus a. In this case, a is a 3. So we are replacing e raised to minus 3t, that's given in the question. Because of that we taken it. Why we taken that e raised to minus 3t? Because it's given in the question. If we are given e raised to 10t there, so we'll take e raised to 10t there. Okay, e raised to 10 of t. So depends on what given, you have to do it one by one. Yes, Rohan is asking why we not multiply e raised to minus 3t inside and then shifting one by one. That is also correct. Both way you are going to get the same answer. Is that? But better to use a shifting only once. Why you apply the shifting one by one separately? Okay, so at the end you are going to get the same answer when you take a common denominator. Okay, you can check, Rohan. You can check that way also. You will get the same answer. So in Laplace transform, the most important part is the observation. When you are given any numerical of a Laplace to evaluate, first you should observe it carefully, decide which property you are going to use it and in which order again. Because there is a combination of exponential function into trigonometry into algebraic also that way. So that time you have to apply two properties one by one. So we'll come to that later on. So right now just we seen shifting property here. So once you complete, tell me, we'll move to the next question. Yes, next question then. Now we have to find the Laplace of g of t. Okay, these questions never asked in the exam. Okay, they never came in the exam in last 5-7 years, but you should know when the function is given in this format, that is a t minus a for t greater than a. You should observe this function is in the form of function is in the form of a second shifting, so we get the answer quickly. What is the other way to do the Laplace of g of t? Anyone? You can find the Laplace of this function in one other way also, but that way is a little lengthy. Can anyone guess? We already done that.
Separating the limit.
Means by definition. Yes, very good. By definition, correct. So if you use a Laplace of the Laplace transform definition and we separate that integral 0 to infinity as 0 to 1 and 1 to infinity and integrate it, that way also you will get it. So without second shifting you can solve that, but that is a lengthy because you have to integrate and you have to apply integration by parts 2 to 3 times there. Okay, but second shifting will give you very quickly that answer. So first I will write the second shifting property. By second shifting I will say here, by second shifting if g of t, okay, I will write this way, g of t is equal to f of t minus a for t greater than a and 0 for t less than a, less than or equal to, doesn't matter, single point doesn't matter in these functions. Then Laplace of that g of t, Laplace of g of t is written as e raised to as into Laplace of f of t. This is the property you should remember then. And now you should observe these, whatever this g of t is in that same format. So is it e raised to minus as or plus as?
No, sir, minus as.
Minus as is there. Okay. E raised to minus as into fs there. That f of s I written as Laplace of f of t. Okay. So now it is a hardly one step then. So from this function, what is f of t minus a? If you compare, so just compare this f of t minus a with this one. So what will be f of t minus a? First of all, what is a first?
Minus
Sir,
1.
1.
Here a is equal to 1. Okay, the first thing a is 1. Okay, now what is f of t minus 1 then? F of t minus a or f of t minus 1? That is a t minus 1 bracket cube. Okay, because a is 1, so compare with f of t minus a. So f of t minus 1, f of t minus 1 is a t minus 1 cube. Is it clear? So what is f of t then? What will be f of
T
t?
T cube.
It is a t cube. So what is the Laplace of f of t?
S cube.
Yes. What will be the Laplace of f of t?
2 factorial upon.
Not
Sorry.
correct. Not correct.
N factorial upon
Okay. Okay.
S
Correct.
S n.
I think it is gamma n plus 1 upon s raised to n plus 1. So it is gamma 3 plus 1. Na? Gamma 3 plus 1 is 3 factorial only. 3 factorial upon s raised to 4. Is it? Which formula we use? Gamma Laplace of t raised to n is gamma n plus 1 upon s raised to n plus 1, or n factorial upon s raised to n plus 1. N factorial means 3 factorial divided by s raised to 3 plus 1. Clear? So what should be the answer then? What is the Laplace of g of t? We got the answer then, one step only. Thus, Laplace of g of t is e raised to minus as. What is the value of a? A is 1. So it is e raised to minus s into fs, Laplace of f of t. What is the Laplace of f of t? 3 factorial. And this is the answer. That's the end of the question. Yes, this is little tricky questions of second shifting. Second shifting is always little tricky there, but you should know what we are doing. So to get a Laplace by second shifting, the first part, what we do here, we compare the given function with the definition of a second shifting. In the second shifting, we say it is f of t minus a. So first part, you should write a. A is 1. A is 1. So f of t minus a, that is f of t minus 1. F of t minus 1 will be t minus 1 bracket cube. We'll find out then from f of t minus 1, we just write f of t. Why we write f of t? Because we want the Laplace of f of t only. This Laplace of f of t only. To get that Laplace of f of t, we replace t minus 1 by t on both sides. We get ft first. F of t is a t cube. And then we calculate Laplace of f of t. At the end, we replace all these values here. Laplace of g of t will become e raised to minus as into Laplace of ft. That will be the answer. Any doubt?
No, sir.
No doubt. Okay, so one last question on the second shifting then. Once you complete it, tell me. I want the answer from you then for the next question. Okay, up to 12:30 already we decided the class is up to 12:30, so just 15 minutes now. Are you completed? Can I show you the next question? Can I show you a next question? No one is there?
Yes, sir.
Okay, good. Yes, now do it your own and tell me the answer. You can write it by observation also. No need to write in the detail in the exam that properties and everything. You can start with f of t minus a, then f of t, Laplace of f of t, and write the answer. So if anyone finished, tell me. So anyone got the answer? One is there.
Sir, e to the power minus pi s
Okay.
into s upon s square plus 4.
Okay, I will write your answer. He's giving the answer like e raised to minus pi s into
S upon s square plus 4.
s square plus 4. Anyone have the different answer? Is there anyone who have a different answer there? I think the answer is correct. Let me check. So we have to do this way. First of all, f of t minus a, or here in solution, we should say by second shifting, because the function is in the form of a second shifting. A is equal to pi. So first thing you will observe, the value of a is a pi from here. Then next, f of t minus pi now. F of t minus pi is cos of 2 times t minus pi. Actually it is f of t minus a. F of t minus a, that is, in this case a is a pi. So f of t minus a or f of t minus pi is a cos of 2 times t minus pi. So this gives us f of t. F of t will become cos, just you replace t minus by only t. So cos of 2t. Cos of 2t. Laplace of f of t. Laplace of f of t is s upon s square plus a square. So s upon s square plus 4. Therefore, Laplace of g of t is e raised to minus as into fs. Okay, e raised to minus as means e raised to minus pi s into fs, and that is the correct answer. Okay, good, very good. Any doubt, anyone?
Last step once again, please.
The last step is by let I tell you the last step. By second shifting, we say Laplace of g of t. Laplace of g of t is e raised to minus as into Laplace of f of t. So this is the formula of a second shifting. So we replace the value of a, which is e raised to minus pi s, into Laplace of f of t. We calculated that we replace s upon s square plus 4. So here, this is the formula of a second shifting. Laplace of g of t is e raised to minus as into fs, or e raised to minus as into Laplace of ft there. Laplace of f of t is itself capital Fs there.
Understood, sir.
Okay.